Hello, this is video number 18 on my Senior Variable Calculus 2. In this video, we're going to talk about improper integrals. There are two different kinds of improper integrals. The first kind is when one of the limits of integration or both of them are infinity or negative infinity, and the second one is when the integrand has a discontinuity. So we'll do examples on both of these. So let's first see what happens when one of the limits of integration is infinity. When the upper limit is infinity, then we take the integral from a to t and we let t go to infinity. And when the lower limit is negative infinity, then we take the integral from t to b and we let the lower limit to approach negative infinity. If this limit exists, then we say the improper integral converges, and also the limit would have to be a finite number, a real number. So let's see what that means. Let's say you have a function and you want to integrate from 1 to infinity. So what does it mean? It means we take the integral from 1 to t and then we let this t to go to infinity. If this area tends to a number, then we say the integral from 1 to infinity of f of x dx converges. And if it approaches infinity, then we say it diverges. Let's do a couple of examples on that. The first one is asking us to evaluate the integral from 1 to infinity of 1 over cube root of x dx. And if it converges, we want to find its value. So let's use what we just learned. So this is cube root of 1 over cube root of x dx. So we write this down as the limit as t approaches infinity, integral from 1 to t, 1 over cube root of x dx. This is the limit as t approaches infinity. Now the integrand is x to the power of negative 1/3 dx. So we're going to have to evaluate this integral by the power rule. We get the limit as t approaches infinity, x to the power of 2/3 divided by 2/3, and then we have to evaluate this from 1 to t. Let's plug in t equals x equals t. We get t to the power of 2/3 divided by 2/3, which is multiplied by 3/2 minus 3/2. Now when t goes to infinity, 3/2 t to the power of 2/3 also goes to infinity. So this diverges. The first integral diverges. Let's see what happens when we do the same thing for the second one. The second one is the integral from negative infinity to 0 of x e to the power of x. So if you look at the integral from negative infinity to 0, x e to the power of x dx, we will have to take the limit as t approaches negative infinity, integral from t to 0, x e to the x dx. How do we integrate x e to the power of x? That is done by integration by parts. So we'll do u equals x, dv equals e to the x dx. So that gives us du equals dx, v equals e to the power of x. So this gives us the limit as t approaches negative infinity, uv, which is x e to the power of x, and then we have to evaluate that from t to 0, minus integral from t to 0 of v, which is e to the power of x, du, which is dx. So the rest of it would be evaluating the integral and then taking the limit. So that's the limit as t approaches negative infinity. When we plug in 0, we get 0. When we plug in t, we get t e to the power of t minus integral of e to the power of x is e to the power of x. We have to evaluate that from t to 0. So this is the limit as t approaches negative infinity, negative t e to the power of t minus e to the power of 0 plus e to the power of t. So we have a negative sign in front, and we also do negative e to the power of negative e to the power of t, so we get e to the power of t. So this is equal to, if you look at this limit, when t approaches infinity, negative infinity, that becomes infinity. When t approaches negative infinity, e to the power of negative infinity is e to the power of negative infinity is 0. So this is infinity times 0. So this is one of those indeterminate forms. So we will have to use L'Hopital's rule, but first we'll have to turn it into a fraction. So let's do that. So we'll rewrite that as negative t, which is infinity, over e to the power of negative t. E to the power of negative t also approaches infinity because negative t approaches infinity. Minus 1 plus e to the power of t. So we will use L'Hopital's rule for this one. Only for the first one though. For the second and third term, we know what they are. So this is minus 1 e to the power of negative t times negative 1. This is by the chain rule. Minus 1 plus e to the power of negative infinity, which is 0. So let's see what we get. For the first one, we have e to the power of negative infinity, negative infinity, so that approaches infinity. In fact, negative infinity, 1 over negative infinity, that's 0. So 0 minus 1 plus 0. So this, in fact, does converge, and it converges to negative 1. Now, what do we do if both limits of integration are infinity? Well, if one of the lower limit is negative infinity and the upper limit is infinity, what we do is we break it down into two integrals, and then if both of them converge, then the integral converges. If one of them diverges, then the integral diverges. Let's look at an example. We are trying to evaluate the integral from negative infinity to infinity of x squared e to the power of x cubed. So first we'll have to evaluate the integral from negative infinity to 0 of x squared e to the power of x cubed dx. If this converges, then we'll also evaluate the integral from 0 to infinity of x squared e to the power of x cubed. And if both of them converge, then we add them up, we get the value of this integral. If one of them diverges, then the integral diverges. So let's do the calculation of this. So we have to do a u substitution for x cubed because the derivative of x cubed, which is 3x squared dx, is right here in front. So we can write this down as the first we have to write it down as the limit. So this is the limit as t approaches negative infinity, integral from t to 0, and then we have x squared e to the power of x cubed dx. Now we're going to use the u substitution that we just saw, limit as t approaches negative infinity, integral. So we have e to the u when x cubed is u, that gives us e to the u. X squared dx is going to be 1/3 du. So this would be 1/3 du. And now if you plug in x equals t, u becomes t cubed. If you plug in x equals 0, u becomes 0. So this would become t cubed to 0. Now let's evaluate this integral. This is limit as t approaches negative infinity, e to the power of u over 3 from t cubed to 0. Let's plug in the endpoints. We get e to the power of 0 over 3 minus e to the power of t cubed over 3. The first term is 1/3 minus e to the power of negative infinity is 0, so that's just 0 over 3. So the answer to this one is 1/3. But that is not enough. We'll also need to evaluate the integral from 0 to infinity of the exact same thing, x squared e to the power of x cubed dx. This is again the limit as t goes to infinity, 0 to t x squared e to the power of x cubed dx. Now we did much of the calculation before. We evaluated this integral as 1/3 of e to the u, but the limits of integration are 0 to t this time. So this gives us limit, or rather 0 to t cubed. Because when x is 0, x cubed is 0. When x is t, x cubed is t cubed. So let's plug it in. We get e to the t cubed over 3 minus e to the 0 over 3. Now e to the t cubed this time is infinity because t approaches infinity. So that means the original integral that we looked at does not converge. Now, how do we deal with the same type of integral when you have a discontinuity? When we have a discontinuity, then we let the limit that has discontinuity to be t, and then we approach that a or b from either the right or the left side of the point b. So let's look at a couple of examples on this one. So the first one is integral from 1 to 2 of 1 over x minus 1 dx. Well, none of the limits of integration are infinity. Therefore, we'll have to see if there is any discontinuity for the integrand. So x equals 1 is a point of discontinuity. So because of that, we'll have to use the limit. So integral from 1 to 2 of 1 over x minus 1 dx. That would be the limit as t approaches 1 from the right, because we are looking at the points inside the interval. That's why we have to approach 1 from the right. Integral from t to 2, 1 over x minus 1 dx. Now integration of 1 over x minus 1 is very easy. So that is the natural log of absolute value of x minus 1 from t to 2. Let's plug in 2. We get natural log of 2 minus 1 minus natural log of t minus 1. As t approaches 1, this guy approaches 0. And natural log of 0 approaches negative infinity. So natural log of 1 is 0 exactly. So that's exactly 0. So we get negative minus infinity. So this means this integral, in fact, diverges. So let's look at the next one. If you look at the next one, the limits of integral clearly are not unbounded. They are not infinity or negative infinity. So we have to look at points of discontinuity. So when is this discontinuous? Well, when we have a 0 at the bottom, we have a discontinuity. So 1 plus cosine of x is 0 at x equals pi, because cosine of pi is negative 1. So then what we're going to do is we're going to take the integral from 0 to pi sine of x over root 1 plus cosine of x dx. And we are going to write this down as the limit as t approaches pi from the left, sine of x over root 1 plus cosine of x, integral of that from 0 to t dx. Now we have to integrate this. Well, we see that the derivative of 1 plus cosine is negative sine, which is up there. So we take u equals 1 plus cosine of x. Du is negative sine x dx. Now the limits of integration are also going to change. When x is 0, u becomes 2. 1 plus cosine of 0 is 2. I have to plug in the endpoints, which is t and 0. So u becomes 1 plus cosine of t. So let's go ahead and evaluate the integral. So this would be the limit as t approaches pi from the left. Integral from 0 becomes 2. So let me change that to 2. And the upper limit is 1 plus cosine of t. Now, the denominator is root u, because I replaced 1 plus cosine of x by u. And the numerator, which is sine x dx, is negative du. So we can integrate this. This is by power rule, easy to integrate. So integral from 2 to 1 plus cosine of t. And this is minus u to the power of negative 1/2 du. So this is going to be equal to the limit as t approaches pi from the left. Integral of that is u to the power of 1/2 divided by 1/2, and there's also a negative sign. This is from 2 to 1 plus cosine of t. So let's plug in the values. We get minus 1 plus cosine of t to the power of 1/2, and then divided by 1/2. and then plus 2 to the power of 1 half divided by 1 half. Let's plug in pi. We get minus 1 plus cosine of pi to the power of 1 half divided by 1 half plus, well, I can bring the 1 half to the exponent to the numerator. We get 2 root 2. And cosine of pi is negative 1. 1 plus negative 1 is 0. So the answer becomes root 2, 2 root 2. So this does converge to 2 root 2. Let's look at the last thing that we're going to talk about in this video. This one is called the comparison property. Assume that you have two functions, and I'm going to illustrate that by a diagram. So assume you have two functions. F is always above g. So we have this one is f. This is y equals f of x. And let me use a different color for g of x. And let's say this is g of x. And the blue one is y equals g of x. So let's assume that always f of x is larger than g of x. Now, if the area underneath the graph of f is finite, if the first integral of f converges, then of course the area underneath the graph of g also converges. So if the larger one is finite, the smaller one would also be finite. If the smaller one is infinity, if the smaller one diverges, then the other one also diverges. Note that this inequality is very important to check before we can apply the comparison property. This is called the comparison property because we are comparing two functions, and we don't need to be able to evaluate integrals in order to use this. Maybe sometimes we cannot evaluate one integral, we compare it with something else that is easier to evaluate, and that's how we get the convergence or divergence of one of the integrals. Okay, so let's look at a couple of examples on this one. We want to determine if each of these is going to be convergent. If we look at 2 plus sine of x over x, this would be less than or equal to 2 plus 1 over x. Sine of x over x is very difficult to integrate. In fact, it's not possible. But we can replace it with 1 and negative 1 to get to things that are easier to integrate. So we get, on one side, we get 3 over x, and on the other side, we get 1 over x. So now, if we can determine 3 over x is finite, the integral of that is finite, the integral of that converges, then we know that 2 plus sine x over x also converges. And of course, 1 over x is positive because x is between 1 to infinity. And if we show that the integral of 1 over x diverges, then the other one also diverges. So let's look at the integral from 1 to infinity of 1 over x dx. This is equal to the limit as t goes to infinity of 1 to t 1 over x dx. Let's evaluate this integral. Well, integral of 1 over x is natural log of absolute value of x, and then we have to plug in 1 and t. So this would give us the limit as t goes to infinity, natural log of absolute value of t minus natural log of 1. Well, as t goes to infinity, natural log also goes to infinity, and natural log of 1 is 0. So that means this integral diverges, but it is smaller than the other integral. So that means the integral that they gave us also diverges. So therefore, this one we use the comparison property. By the comparison property, the given integral, the integral from 1 to infinity of 2 plus cosine of x over x dx also diverges. Okay, so we'll do one last example on this one, and then we will summarize. So let's look at the other integral. The integral from 0 to infinity of e to the power of negative x squared dx. So this is one of those integrals that cannot be evaluated. You cannot really integrate this one. But we can compare this with something that is simpler and easier to evaluate. Well, if you look at x squared is more than x if x is more than 1. So that tells us that negative x squared is less than negative x. What is the benefit of this? The benefit is we can integrate e to the power of negative x. So we can say, well, the integral from 0 to infinity of e to the power of negative x squared dx is equal to integral from 0 to 1, because I'm looking at the interval from 1 to infinity. I'll break up the first piece. The first piece, this is a finite number, so that doesn't really matter. But the second piece can be compared. This is 1 to infinity of e to the power of negative x squared dx. We can compare this one with e to the power of negative x. So we know e to the power of negative x squared is less than e to the power of negative x, and of course they're both positive if x is more than 1. So what does it mean? It means if I look at the integral from 1 to infinity of e to the power of negative x dx, if this is finite, then the other one would also converge. The other one would also be finite. This is the limit as t goes to infinity, integral from 1 to t e to the power of negative x dx. Now we can easily integrate e to the power of negative x. The integral becomes e to the power of negative x over negative 1 from 1 to t, and this time t goes to infinity. Let's now plug in the values and then take the limit. We get the limit as t goes to infinity. Plug in t, we get e to the power of negative t over negative 1, and then plus e to the power of negative 1. Well, as t goes to infinity, this goes to negative infinity. E to the power of that goes to 0. So the whole thing becomes 1 over e, which is a finite number. So this converges. Therefore, by the comparison property, the other one also converges. So by comparison property, the given integral of e to the power of negative x squared also converges. And we know that we can start from 0 because the integral from 0 to 1 is already a finite number. So to summarize, in this video we learned about two different types of improper integrals. The first type is the one that one of the limits of integration or both of them are infinity or negative infinity. And the second type is when you have discontinuity at either a or b. We turn both of these into limits, and then we evaluate the integrals and we take the limits. And in the process, you might have to use any of the techniques of integration that we have learned before, or any of the techniques of finding limits like L'Hopital's rule. And finally, comparison property tells us that if you have two functions, one larger than the other and both of them positive, if the integral of the larger one converges, the integral of the smaller one converges. If the integral of the smaller one diverges, then the integral of the larger one also diverges. And that brings me to the end of this video. I will see you in the next video.